Hello everyone, welcome to Physics 205. So in this video, what I want to do is go over the in-class practice problems for projectile motion. Okay, so this first question says a student stands at the edge of a cliff and throws a stone horizontally, right? So at 0 degrees over the edge with a speed of 18 meters per second. The cliff is 50.0 meters above a flat horizontal beach. How long after being released does the stone strike the beach below the cliff? So what's the time it takes to reach the beach below? And then with what speed and angle of impact does the stone land? Like what is the stone's velocity? What it means when it says land is like just before it hits, like instantly before it hits. Okay, so what I would do is I would draw a picture here. So we have this cliff, and we know that the height of this is 50, right? This height is 50.0 meters. The stone is thrown horizontally, right? So at like 0 degrees. And we know that initial velocity. So in the x direction, the initial velocity is going to be, I guess it's 18, right? 18.0 meters per second. Because it's thrown horizontally, that means the initial velocity in the y direction will be 0. Right? If you look at that velocity vector, initially all of it is in the x direction, none of it is in the y direction. I'm assuming that I have the standard, x is pointing to the right and y is pointing vertically upward. Okay, what else do we know? Well, this thing is going to immediately start to fall, right, due to gravity, and it's going to hit at some time. We need to figure out the time, and we also want to figure out the velocity at which it hits at. So we want to figure out this velocity here, this like final velocity. And it's going to consist of an x component, like a vx, and it's also going to consist of a vy here. Right, and then we can figure out the magnitude of v, and we can also figure out this angle here. And we could say it's like, south of east or whatever the angle is. Okay, what else do we know? Well, because there's no forces acting, right? It's projectile motion. We're assuming there's no air resistance. There's no forces acting in the x direction. Then that final Vx, that must equal the initial velocity in the x direction, which is, because it's constant, right? Which is 18.0. Remember, in the x direction, the velocity of a projectile is constant. It stays the same in the x direction. All right, what else do we know? Well, we know that this change in height, right? If this is my final position in the y direction and this is my initial position in the y direction, what is that change in height? That change in height, so delta y, must be negative 50. Right? Remember, changes, this is like y final minus y initial. You can think of y final as being 0, right? If this is 0 height, and then y initial is being 50, and if you do 0 minus 50, you're going to get negative 50. Right? So the change in the y position, the displacement in the y direction, is negative 50 meters. Okay, do we have enough information here to figure out the time? Yes. If we use the y direction, we can figure out the time, right? Because we know this equation. We have delta y equals v naught y delta t minus 1/2 g delta t squared. V naught y is 0, right? So that term is 0, right? There's no velocity in the y direction. And then if I plug in here, this is negative 50. This is going to be negative 1/2 times 9.8 times delta t squared. So that's going to be negative 50 is equal to, what's that, negative 4.9, I guess, delta t squared. So if I divide by negative 4.9, both sides, I'm going to get delta t squared is equal to whatever that is. Let me do this out quickly. So negative 50 divided by negative 4.9. I'm going to get 10.2. And then if I take the square root of both sides, remember we want the positive root, right? Because it's a positive time. Delta t here is going to be around 3.19. So square root of 10.2 is around 3.19 seconds. Okay, so that's how long it takes this object, this stone, to hit the beach, right? To hit the ground. 3.19 seconds. All right, what about the second part of the question? What is this? What is the velocity right before it hits? What's the magnitude and direction of velocity? Well, if we can find the components of the velocity, right, then we can figure out the velocity itself. The x component I already know. Remember, the x component is the same as the initial, right? We did that here. The Vx is simply going to be 18.0, same as what it was initially, because it doesn't change in the x direction. So we have that. How do I figure out Vy? Well, Vy I can figure out from my constant acceleration equations, right? My free rise, free fall equations. Vy is going to be V naught y, which is 0, minus g delta t. So Vy, this is 0, minus 9.8 times 3.19. And that's going to be negative 31.26. Makes sense it's negative, right? Because in the y direction, the velocity right before it hits is going to be negative something, right? It's pointing downward, negative something. Okay, so now what I could do is now take this right triangle here. Oops. Getting these stray marks by accident. Sorry about that. Okay, so I could take this this right triangle for the velocity here. Let's see. I know Vx is 18, right? So this is 18, that side. And we just said Vy is negative 31. So that means the length of this side, I don't need the negative anymore because I'm just dealing with a triangle. So the length is 31.26. I want to figure out what this magnitude is, V, and I want to figure out what this angle is, theta. Well, to figure out V, I can use Pythagorean theorem, right? So V is simply going to be the square root of the x component squared plus the y component squared. And if you work that out, that turns out to be 36.1 meter per second. Okay, so that's the magnitude of velocity right before the stone hits. And in what direction is it traveling at? Well, to figure out theta here, I can use inverse tangent, right? Inverse tan of opposite over adjacent. And that turns out to be around 60.1 degrees. And we could say south of east, right? To make sure that we know that we're talking about that fourth quadrant. Okay, so that's the velocity vector right before it hits. It has a magnitude of 36.1 and it has a direction of 60.1 degrees south of east. Okay, second question. A fireman 50.0 meters away from a burning building directs a stream of water from a ground level fire hose at an angle of 30.0 degrees above the horizontal. If the speed of the stream as it leaves the hose is 40 meters per second, at what height will the stream of water strike the building? Okay, so again, let's draw a picture here. Here's the ground. Here's the building. We have this stream of water that's leaving the ground at this point at a velocity of 40 meters per second. And we know this angle, right, is 30 degrees. And the stream of water is going to like rise to a peak and then somehow at some point hit the building here, right? And we want to figure out how high above the ground that it strikes that building. So we want to figure out this height here, right, that h. Okay, so first thing I would do is I would figure out the components of this initial velocity vector, right? We want to figure out the x component, because typically you're going to need both. So this is like v naught x, and I want to figure out the y component. If I project it onto the y-axis, this would be like v naught y. You're almost always going to need both of them, so it's just good to compute them right off the bat. So if we use this right triangle here, right, we know the angle is 30 degrees. I know the hypotenuse is the magnitude of the velocity is 40. And I'm looking for v naught x, v naught y. So since the x component is adjacent, right, that's going to involve cosine, and the y component will involve sine. And they're both going to be positive in this case, right? So this is going to be 40 times cosine of 30. That turns out to be 34.64 meters per second. And then v naught y is 40 times sine of 30. And that turns out to be, sine of 30 is a half, right? So this is going to be 20 meters per second. So I would do that first. What else do we know here? Oh, we know this, right? We know that this distance from where the water leaves to the edge of the building, this is like delta x, that's 50 meters. We could figure out the time now too, right? So in the x direction, right, there's no acceleration, so we know delta x is going to equal v naught x delta t plus 1/2 ax delta t squared, but ax is 0, right? There's no acceleration in the x direction. Or again, you could use the fact that the average velocity in the x is delta x over delta t. But again, since there's no acceleration, the average velocity is a constant velocity, right? Either equation gives you the same results. So using that, though, we could figure out the time. So the time, if I solve for delta t here, it's going to be delta x divided by my initial velocity, which is the same as my average velocity, right? Because it doesn't change. So if you work that out, this is going to be 50 over 34.64. And if you work that out, it's 1.44 seconds. So now I know how long it takes. So when it leaves the hose here to when it hits the building, it's going to take 1.44 seconds. So now actually to figure out the height that it hits above the building, what I want to find now is what is delta y, right? This is going to be the same as delta y here. Delta y is the height at 1.44 seconds, right? I want to find the change in that height at that time. So if I use this equation, delta y is the initial y delta t minus 1/2 g delta t squared, right? Because it's a free rise, free fall in the vertical direction. And then I can just plug in, right? Everything else I have. So delta y is going to be v naught y, which is what? 20, I believe. Yeah, 20. The time was 1.44 minus 1/2. G is always 9.8. And then 1.44 squared. And if you work that out, that turns out to be 18.64 meters. So that's how high up the wall the water will hit the building, right? 18.64 meters. Okay, next question. You're told a quarterback throws a football toward a receiver with an initial speed of 20 meters per second at an angle of 30 degrees above the horizontal. At that instant, the receiver is 20 meters from the quarterback, okay? In what direction and with what constant speed should the receiver run in order to catch the football at the level at which it was thrown? Great. We need to definitely draw a picture, see what's going on here. Okay, let's say, so this level is going to be the level that the football is thrown at. And let's say, well, we know it's thrown with a velocity of 20, right, meters per second. And we know this angle was 30 degrees. Okay, and I'm going to say that this location is like at 0, just to keep it simple. The receiver is starting at 20 here. And this football, let's say, I mean, I don't know exactly, it could go closer, it could go further, but it's going to do something like this, right? It's going to rise to a peak. Let's say it goes further. And then let's say it lands here at some position. So this receiver would have to run in this direction in a certain amount of time to catch the ball there. Okay. All right. So to start, let's first find the components of that initial velocity. So I want to find v naught x, because typically that's what you do first with these problems, right? I want to find v naught x, and then if I project it onto the y-axis, this is like v naught y. So again, if I use this right triangle here, this is 30 degrees. This hypotenuse is the magnitude, right? The speed that it leaves the quarterback's hand. So that's 20 meters per second. I'm looking for v naught x, v naught y. We've done this a billion times, right? We know v naught x is going to be 20 times cosine of 30, which ends up being like 17.32 meters per second. And then v naught y is 20 times sine of 30 degrees. And that's going to be 10 meters per second. Okay. What I probably want to do now is I want to figure out the time it takes to travel this distance, which I don't even know yet, right? So this distance right here is going to say be delta x, right? The distance that the football travels. And I want to figure out the time that it takes. Once I figure out the time that it takes, since I know the velocity in the x direction, I could figure out this delta x. Okay, so can we use the y information to figure out the time? Yes, because there's something else I know here. I also know that the change in the y position, right, the y displacement is 0, right? Because it's taking off at this height and it's landing at the same height. Like the final position in the y minus the initial position in the y is 0. So delta y is 0. So I could use that to figure out the time, right? So if I plug into this equation, I know that delta y is equal to v naught y delta t minus 1/2 g delta t squared. So if this is 0, this is going to be 10 delta t minus, and then 1/2 times 9.8 is like 4.9 delta t squared. I can solve this, right? I could factor out a delta t, and I have left 10 minus 4.9 delta t. So one possibility is delta t equals 0. All right, that's one solution. And the other solution is 10 minus 4.9 delta t is equal to 0. The first solution just says that the football will again be at 0 height. It'll be the height that it leaves at and the height that lands at will be the same in 0 seconds, which is kind of the solution that we don't want, a trivial solution. We want the one where it ends up at the final height is the same as the initial height, but we want this time. So that's going to be this part, this solution here. So if we solve that, let's see, we're going to get 4.9 delta t is equal to 10. If I divide by 4.9, I'm going to get delta t is equal to 2.04 seconds. Okay, so that's the time that the ball is in the air. So how far did the ball travel? What is this delta x equal to? Well, now we can figure that out, right? Because again, we know that delta x is equal to v naught x delta t. There's no acceleration. I don't need the rest of that formula because there's no acceleration in the x direction, right? We're assuming there's no air resistance. So if I plug in v naught x was 17.32, and now I know delta t is 2.04, that's going to be like 35.33 meters. Okay, so if this is, so now we know this, right? I can erase that question mark. This is going to be 35.33 meters. So now I can figure out how far the receiver had to run, right? I can figure out that distance. How do I figure out that distance? Well, that distance must be 35.33 minus 20. Remember, that receiver started at 20, and then we're going to run to catch the ball. So the distance that they had to travel was going to be 15.33, right, meters. Okay, now we need to find the speed. Remember, the whole goal was to find how fast the receiver had to run. Well, we know the time, right? The total time. So the receiver is going to leave this position at 20 and run to this position at 35.33. So the receiver is running this distance of 15.33 meters. And what time are they running it? Well, they're running it in the total time that the football is in the air, right? They're running it for that same time that we just found, which is, what was it, 2.04 seconds. Okay. So we know that the average velocity, we're assuming it's going to be constant, of the receiver is going to be the displacement of the receiver, which is d in this case, I'm calling it d, divided by that time, divided by delta t. So if I plug in 15.33 divided by 2.04 seconds, then that's going to be 7.51 meters per second. So that's how fast the receiver has to run. And he has to run in the direction the ball was thrown, right? Because it's going to land, we just calculated it. Since delta x was greater than 20, was like 35.33, then the receiver has to run in that direction, the same direction that the ball was thrown in. Okay, we weren't asked that, but I'll write it here. So the receiver runs at 7.51 meters per second in the direction the ball was thrown. Okay, so not bad. Some of these problems you really have to think about, right? We're just using those same equations, those same constant acceleration equations for the x direction and then for the y direction if we have free rise, free fall motion. But sometimes you have to draw pictures and think about like what is really being asked here. Okay, last question. So in this case, you're told a basketball player is running at 5.00 meters per second directly toward the basket when he jumps into the air to dunk the ball. He maintains his horizontal velocity. So that 5.0 meters per second is his horizontal velocity. What vertical velocity does he need to rise 0.75 meters above the floor? And then how far from the basket, measured in the horizontal direction, must he start his jump to reach the maximum height at the same time he reaches the basket? Okay, so a bunch of questions here. I'm gonna draw a picture. Here is the floor, right? Here is the basket. So something like that. And then this person, so let's say this is the center of mass. It's gonna, so he's gonna jump off the floor, right? And he has some velocity. And we actually know that the V naught X here is 5. And we want to figure out what his vertical velocity would have to be, v naught y. So this is v naught y. And the key thing is that the person is going to like rise up, and then right when they hit the basket, we're going to assume they're at the highest point. Yeah, so what vertical velocity does he need to rise exactly like 0.75 meters above the floor? So we also know this, right? We know that this, from where his center of mass starts, right, where he leaves the ground with that velocity, that this distance here, so from the basket to that point, that's delta y, which we know in this case is 0.75. Okay, so we know a bunch of things, right? I'm going to write them down here again. We know v initial x is 5, that was given, meters per second. We know delta y is 0.750 meters. Yeah, okay. So we don't know v initial and the y, right? We're looking for that v initial and the y. And we don't know the time actually that it takes to reach that max height either. We can figure that out later. All right, so let's answer the first question. What vertical velocity does it need to rise 0.75 meters above the floor? Well, if you look at your constant acceleration equations in the y direction, we can use this one, right? Vy squared equals v initial y squared minus 2g delta y. Why can we use that? Because we're assuming that when he reaches the basket, he's at the highest point, right? He's not going to go anymore. So what is his velocity at that point? So what is Vy? That's 0. Right? In the y direction, at the highest point, which is going to be at the basket, he's like instantaneously at rest, right? Just for an instant, he has a velocity of 0. So we can use that here now, right? If this is 0, so I have 0 squared is equal to v naught y squared minus 2g delta y. Then I can bring this term right to the other side. I can add 2g delta y to both sides. So I have v naught y squared is equal to 2g delta y. And finally, I can take the square root of both sides. And we know since he's jumping up, moving up, we want the positive root, right? So v naught y will be positive square root of 2g delta y. Okay, so if we plug in, this is going to be 2 times 9.8 times 0.075. And I want the square root of that. If you work that out, you're going to find that you're going to get 3.83 meters per second. So that is the vertical velocity that he took off at. Right, so this velocity upward is 3.83 meters per second. By the way, if we wanted to, we could find his total speed, right, of this vector here, and we could find the angle, because now we know the x component, we know the y component, right? The x component is 5, the y component is 3.83. We could find this angle and we could find the magnitude of his actual velocity here. But we weren't asked that, so we won't have to worry about that. But we could find it if we wanted to. Okay, what else do we need now? So now we need to figure out this delta x, right? We don't know how far. So that's the other thing we don't know, delta x. So from when he leaves the ground to the basket, that's delta x. We need to figure that out. Now, do we know the time that he's in the air? No, but we can figure it out, right? Using the y direction. So what I would do is find the time. to reach the max height, which was right at the basket. How can we do that? Well, we could use this equation, right? Vy equals V naught y minus G delta t. Again, at the highest point, the velocity is 0. Right? At the max height, the velocity is 0, the basket. The velocity, just for an instant, is 0. And then I could solve this for delta t. Right? So if I add this term to both sides and then divide by g, I'm going to get delta t is equal to, it'll be V naught y divided by g. So if we work this out, this is 3.83, that's what we just found, divided by 9.8. Looks like it's going to take around 0.391 seconds to get to that peak height. Okay, so how far does he travel horizontally, right, during that time? Well, we know the initial velocity in the x direction was 5, and we know the time, so we can figure out delta x. Right, so now remember, in the x direction, we can use this equation. Okay, we don't have the, remember the whole equation is this. But because we're talking about a projectile, in the x direction, ax is equal to 0, right? Meters per second squared. There's no acceleration in the x direction. We're assuming there's no air resistance, no forces. So that's why we don't ever include that for the x direction. It's simply delta x equals v naught x times delta t. So in this case, the v naught x was what, 5? And the time that they're in the air is 0.391. So that means delta x is going to be like 1.96 meters. So horizontally, if I go back to the picture here, that's how far they've traveled, right? From when they left the ground, their center of mass traveled horizontally 1.96 meters, right? Until when they're at the basket. Okay, so again, nothing more than, a projectile problem, except you had to think about like what was going on. It's really helpful to draw pictures, write down what you know, what you're looking for, and then always keep that kinematic sheet that I made for you guys handy so you have all those formulas. Okay, great. Thanks.